Hi, my name is Walker Gallman, and this is my Lab 3 report on circuits. The purpose of this lab was to predict the behavior of circuits with resistors, use multimeters to measure the values of current and potential difference, and to examine the behavior of resistors and capacitors. The main results from this lab in part 1 include the prediction of current at 20.4 milliamps, and it was measured at 19.5 milliamps. The calculated resistance for the 47 ohm resistor was 48 ohms, and the 100 ohm resistor was 102 ohms, and the resistance in both the wire and ammeter was estimated and rounded down to 0 ohms. Results from part 2, the time trial for trial 1 was 1 minute and 33.62 seconds, and the time for trial 2 was 55.14 seconds. This lab was based on key circuit principles, including the general conservation of energy and charge, and furthermore, the Kirchhoff's circuit laws, both the loop rule, which is the sum of potential differences in a closed loop is zero, and the node rule, the sum of current entering a junction equals the current exiting a junction. Also, Ohm's law, which is the voltage, is equal to the product of the current and resistance, and capacitance, which is equal to the charge divided by the voltage. For results and observations, part 1, we analyzed a circuit with the following parameters. It was a system the system is a closed circuit with surroundings being the earth and air. It had two 1.5 volt batteries, two resistors, one with 47 ohms and one 100 ohm resistor, and two ammeters. Predictions, according to the node rule, which states that the first or charge I1 is equal to current I1 is equal to current I2. And the total resistance is equal to the sum of the resistance of each resistor, meaning total resistance is 147 ohms. And using Ohm's law and rearranging to solve for current, the predicted current was estimated to be 20.4 milliamps. And the actual measured current was close in value and was measured to be 19.5 milliamps. After replacing an ammeter with a voltmeter, the potential difference across the open circuit was 3 volts and the current was 0 amps. This is because an open circuit prevents circuit current flow, so the potential difference must equal the battery voltage, which is from Kirchhoff's loop rule. The ammeter reading remained unchanged when using the voltmeter. Since voltmeters have high resistance, they draw negligible current, leaving the circuit path unaltered. And with a graphical representation in the bottom left, the potential difference increased to 3 volts across the battery, and it dropped across the resistors, eventually returning back to 0 volts. The 100 ohm resistor had a steeper potential drop than the 47 ohm resistor. For the parallel circuit analysis, when connecting an ammeter in parallel with the 100 ohm resistor, it caused the current to increase to 0.06 milliamps. This happened because less current flowed through the 100 ohm resistor, and since the current split at the node by the node rule. The ammeter had 0 ohms of resistance, producing the effective resistance and increasing the overall current. The actual resistance values were higher than expected due to the low precision of the ammeter. The 47 ohm resistor was estimated to be 48 ohms, the 100 ohm resistor was estimated to be 102 ohms, and the resistance in the wire and ammeter was rounded to be 0. For part 2, we analyzed a circuit containing 110 ohm and 120 ohm light bulb, a 9 volt battery, and 200 mF capacitor. When charging, the bulb initially glowed brightly, then dimmed as the capacitor charged. The current decreased from its maximum to 0. And when discharging, after disconnecting the battery, the bulb lit up again and then faded as the capacitor discharged. And again, current changed. It decreased from maximum to 0. The time for bulb 1 was 1 minute and 33.62 seconds, and the time for bulb 2 was 55.14 seconds. Assumptions for this lab include that the resistance in both the ammeter and wires were negligible. However, in reality, there is resistance in both, as there is no material with a 0 resistance. For potential errors in the lab, we neglected resistance in the wires and ammeters, meaning this could be a cause for variance between reality measurements and ideal measurements. Additionally, the measurements were not exact due to rounding and simplification for analysis. For the question, what if you charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict that the capacitor would reach full charge, and would this prediction happen in real life? In an ideal model, a capacitor would charge instantly or instantaneously when connected directly to a battery with no resistor, because the sum of the voltages around the loop must equal 0, satisfying Ohm's law. With 0 resistance, the current would theoretically be infinite, instantly charging the capacitor until the voltage matches that of the battery. However, in real life, this does not happen because no material has exactly zero resistance. Even the wires in the circuit, though having low resistance, still introduce some opposition to current flow. As a result, while the capacitor will charge very quickly, it will not do so instantaneously. And an ammeter can be used to measure the slight delay in charging time. General conclusions from this lab include: to obtain accurate values in an ideal circuit, wires and ammeters must have negligible resistance. The current and voltage in RC circuits are time-dependent and decreases exponentially over time, and Kirchhoff's laws, the node and loop rules, are essential tools for analyzing circuit properties. Thank you.